Long before the Atlantic and Pacific looked the way they do today, Earth kept rebuilding its oceans into worlds that seem almost impossible. One sea cut North America in half while giant reptiles hunted above a seafloor where the oxygen could disappear. Another covered part of the Arctic in a living green surface. And much farther back in time, the ocean was divided into chemical layers with breathable water near the light, poison beneath it, and an iron-rich abyss below that. These were not alien planets. Every one of them existed right here on Earth. And the farther back we go, the more terrifying the oceans become. The sea across America. Around 94 million years ago, if you stood in the middle of Kansas, there would be no wheat fields, no roads, and no horizon of dry land. You would be floating in an ocean. Global sea levels were so high that water from the Gulf of Mexico pushed north through the center of North America and connected with the Arctic. The continent was split into two enormous landmasses by a shallow marine corridor called the Western Interior Seaway. And this sea was full of predators. Enormous fish patrolled the open water. Long-necked plesiosaurs hunted below the surface. Later in its history, mosasaurs turned the seaway into a feeding ground for some of the most powerful marine reptiles ever to exist. But the real nightmare was underneath them. At times, the upper water could be crowded with life while the seafloor below was running out of oxygen. The more productive the surface became, the more dangerous the depths could become. The process began far away with massive volcanic activity. Greenhouse gases warmed the climate and nutrients poured into the sea. Microscopic organisms exploded near the surface. When they died, their bodies sank into the darkness. Then bacteria began consuming them. But decomposition needs oxygen. As billions of tiny bodies fell through the water, bacteria used the oxygen faster than currents could replace it. In the most affected regions, the bottom water became a suffocating dead zone. Imagine escaping a giant predator by diving deeper. The sunlight fades, the water becomes darker. But instead of finding safety, every breath becomes more difficult, because the water itself can no longer support you. The entire seaway was not dead at the same time. Conditions shifted from place to place, but wherever the oxygen collapsed, much of the life on the bottom had nowhere to go. Dark organic mud collected in silent layers beneath the living sea. Over millions of years, that mud became black shale, preserving the chemical scar of an ocean that could be alive on top and nearly uninhabitable below. It was a world where life at the surface helped create death on the floor. But the next ocean hid its danger beneath something far stranger than dark water. The green Arctic. Around 50 million years ago, the Arctic was not frozen. There were no permanent ice sheets covering the pole. The climate was warm enough for forests to grow at high northern latitudes, while rain and rivers constantly poured into a restricted Arctic Ocean. From a distance, parts of its surface may have looked less like an ocean and more like an endless green wetland. Floating across the water was Azolla, a tiny freshwater fern. Today it forms dense mats on ponds and quiet lakes. But its fossil remains have been recovered from ancient sediments in the middle of the Arctic Ocean. That creates a bizarre image, a warm polar sea with patches of living green vegetation spreading across its surface. But Azolla could only thrive if the upper water became fresh enough, and that meant the ocean was beginning to separate into layers. Fresh water is lighter than salt water. Rain and river runoff could form a low salinity lens that floated above the heavier marine water. At least during repeated episodes, this green surface layer became stable enough for enormous amounts of Azolla to grow and reproduce. Now imagine falling through it. You break through a carpet of small green leaves. Beneath them, the water changes. The surface is fresh or brackish, but the deeper you sink, the saltier and darker it becomes. And because the surface layer can slow mixing, oxygen from the atmosphere has a harder time reaching the water below. The peaceful green ceiling becomes a lid. The evidence does not show one solid fern carpet covering the entire Arctic. Some Azolla may have been washed in from surrounding land, and the strongest freshwater conditions may have been limited to part of the basin, but the real version is already strange enough. a marine ocean wearing a temporary freshwater skin. From above, it could look alive, lush, and almost inviting. Underneath, the green surface concealed a darker world cut off from the air. And even this ocean was stable compared with the next one because the next sea began to disappear. The Vanishing Megalake. During the Miocene, a vast body of water stretched across Eurasia. It covered huge areas that are now dry land from Central Europe toward Western Asia. This was Paratethys, a marine world filled with islands, reefs, and warm coastal habitats. Then tectonic movement began closing its connections to the global ocean. The sea became trapped. At first, Paratethys was still enormous. It eventually formed the largest megalake known from the geological record. But without a stable connection to the open ocean, its future depended on a dangerous balance between rivers, rainfall, and evaporation. When that balance failed, the shoreline moved, not by a few meters, not beyond a single beach. It retreated across entire regions. One scientific reconstruction identifies 4 major regressions between roughly 9.75 and 7.65 million years ago. During the most extreme of them, Paratethys may have lost around 1/3 of its water and close to 70% of its surface area. Imagine living beside a sea that has always filled the horizon. Then, generation after generation, the water pulls away. Islands connect to the mainland. Bays become isolated lakes. Vast areas of former seafloor rise into open air. The water that remained did not form one normal lake. A salty central basin could survive while fresher water collected around the margins. Animals adapted to one part could become trapped as the chemistry changed around them. Earlier, central Paratethys had supported a spectacular subtropical ecosystem. Reefs grew between islands and hundreds of species occupied its different habitats. Then, cooling, falling water levels, fragmentation, and oxygen-poor bottom water destroyed many of those environments. The exact timing and cause of every regression are still debated, but the transformation itself was real. A sea became a megalake. The megalake broke into compartments, and those compartments eventually left descendants such as the Black Sea, the Caspian Sea, and the Aral Sea. Paratethys did not destroy its world with a single giant wave. It did something slower. It moved the water away, changed the salt, and left entire ecosystems stranded behind the retreating shore. But another ancient ocean faced the opposite nightmare. Instead of losing water, it was overwhelmed by what poured into it. The ocean under endless rain. Around 234 million years ago, nearly all of Earth's land was joined into the supercontinent Pangaea, surrounded by the greatest ocean on the planet, Panthalassa. Much of Pangaea's interior was hot and dry. Then a chain of enormous volcanic eruptions began changing the atmosphere. Carbon dioxide rose, the planet warmed, and the water cycle accelerated. Regions that had been arid were struck by repeated intervals of intense rainfall. Rivers swelled across the continent, tearing minerals and nutrients from the land and carrying them toward the sea. At the surface, this could trigger an explosion of life. Plankton multiplied in the warm, fertilized water. But once again, the abundance above created a disaster below. The plankton died, their remains sank, bacteria consumed them, and the deep water began losing oxygen. Rocks formed in what was once equatorial deep Panthalassa preserve evidence that the water became chemically reducing during this event. Fossils also record a major turnover among conodonts, small eel-like marine animals whose tooth-shaped remains survived in the sediment. Picture this ocean during one of the great rain pulses. Storms hammer the surface. Rivers stain coastal water with sediment. The upper sea blooms with microscopic life. But far beneath the waves, the oxygen is being quietly consumed. Nothing has to chase you. Nothing has to bite you. The danger spreads invisibly as the habitable part of the ocean becomes thinner. Scientists are still determining how much of Panthalassa was affected and for how long. It was not necessarily one global dead ocean. But the chain is preserved in the rock. Volcanism heated the planet, rain stripped nutrients from the land, life exploded near the surface, and the deep sea began to suffocate. It was an ocean poisoned by its own abundance. And the next sea proves that an ocean does not need poison to become another world. Sometimes all it needs is an open door. The ocean gateway switch. Around 174 million years ago, a long marine corridor connected the warm Tethys Ocean in the south with the colder Boreal Sea in the north. This narrow passage acted like a valve between two different ocean worlds. As the continents shifted and the gateway changed, cold water was able to push through routes that had once carried warmer currents. In the studied corridor, seawater temperatures may have fallen by as much as 10 degrees Celsius. There would be no wall of ice announcing the change, no tidal wave, no warning visible on the horizon. The invasion would be almost invisible. Imagine a warm marine habitat filled with animals adapted to one stable climate. Then a new current arrives. The water surrounding them grows colder. Food webs shift. Familiar breeding grounds change. Species that cannot move or adapt are trapped inside an ocean that now follows different rules. Temperature controls almost everything in seawater. It changes how much oxygen the water can hold, how quickly animals grow, where plankton can survive, and which currents carry nutrients through the sea. So a change in one gateway could reorganize habitats far beyond the passage itself. The 10-degree estimate does not describe the entire global ocean. It belongs to the ancient corridor recorded in the study. But in that corridor, tectonics did not simply redraw the coastline. It reached into the water and changed the climate from inside. An ocean can look the same from above while becoming a completely different world below. And in the next world, even the deep ocean behaved in a way that would feel impossible today. The Hot Ordovician Abyss. In the modern ocean, the deepest water is freezing cold. It forms near the poles, sinks, and slowly spreads across the seafloor. But around 450 million years ago, parts of the Ordovician Ocean may have worked in reverse. This was a greenhouse world with broad shallow seas covering the continents. Near the surface, marine life was expanding into spectacular new forms. Reefs and shelled animals occupied the sunlit water. Far below them, warm, salty water could sink into the abyss. Strong evaporation made tropical seawater extremely salty. Salt increased its density enough to pull it downward, even while the water remained warm. If you descended into this ocean, you would expect the temperature to fall. But the deep water could remain strangely warm. And that warmth carried a hidden danger. Warm water cannot hold as much oxygen as cold water. As dense salty water filled the depths, the oxygen available to animals on the seafloor could shrink. Organic remains falling from above entered a dark world with fewer creatures able to consume them, helping create the organic-rich sediments found in parts of the Ordovician record. This does not mean the entire Ordovician Ocean was dead. Its shallow seas supported an extraordinary expansion of life. That contrast is what makes it disturbing. Above you is a bright marine world crowded with new animals. Below it is a warm, heavy abyss where oxygen becomes harder to find the deeper you go. It was an ocean with a thriving roof and a suffocating basement. But even that abyss still contained water we would recognize. The final ocean was divided into chemical worlds. The three-layer ocean. Around 1.8 billion years ago, Earth already had oxygen near its surface. But the ocean was nothing like the stable blue world we know today. If you could lower a camera through this ancient sea, the planet would change color in layers. Near the top was a thin refuge touched by sunlight and oxygen. This was the most familiar part of the ocean, but it did not extend very deep. Below it, the oxygen disappeared. In some waters along the continental margins, microbes filled the middle layer with hydrogen sulfide. This was not simply dirty water. Hydrogen sulfide attacks the system's many complex organisms used to release energy. For most modern animals, entering enough of it would be fatal. And beneath that poisoned middle zone was another ocean entirely. The deepest water was anoxic and rich in dissolved iron. Without oxygen to force that iron out of the water as rust, it could remain suspended in the dark abyss. So the ocean was not one uniform poisonous soup. It was more terrifying than that. It was a stack of separate chemical habitats. Blue and oxygenated near the light, sulfidic in parts of the middle, dark, iron-rich, and airless in the depths. The boundaries between these layers could move. If sulfidic water rose toward the surface, a previously habitable zone could become hostile without any predator arriving. The danger was not an animal. It was the invisible chemistry of the ocean climbing toward you. Imagine sinking through it. First, the bright surface disappears above your head. Then oxygen collapses. The water enters a chemical world dominated by sulfur. Deeper still, the ocean becomes an iron-rich abyss unlike anything covering Earth today. There is no monster waiting at the bottom. The ocean itself is the monster. And that is what makes these prehistoric seas so disturbing. Each one found a different way to become hostile. The Western Interior Seaway hit a dead floor beneath giant predators. The Arctic covered marine water with a green freshwater skin. Paratethys pulled away from its own shores. Panthalassa suffocated beneath the consequences of endless rain. A Jurassic gateway changed the temperature of an entire corridor. The Ordovician Ocean sent warm, salty water into the abyss. And the Proterozoic Sea divided itself into layers of oxygen, poison, and iron. Earth did not have one ocean that slowly became the ocean we know. It built different ocean worlds again and again. And the blue sea covering our planet today is only the latest version.